problem. We have a solid conducting sphere of radius r. It has a net charge q. We want to find the electric field energy density at a distance r from the center of the sphere, both inside and outside. We want to find the total electric field energy associated with the sphere. How much work does it take an external force to get the charge q on the surface of the sphere? Then we also want to find the capacitance of the sphere. So let's get started. We'd like to find the electric field energy density. So that's a lowercase u. Sometimes we put a subscript of E on there, and that's the energy divided by the volume. The electric field energy density is the net energy over volume, so capital U divided by the volume. And what we mean by volume is the volume of where the electric field is established. We can work this out to find that the electric field energy density is 1/2 times our constant epsilon naught. We use epsilon naught instead of epsilon because we're dealing with a vacuum here. We don't have a dielectric. Times the electric field squared. So we'll start by drawing our sphere. So this is a conductor. It has a net charge q. When we have a conducting sphere, we ask where does the charge reside, and it has to reside on the surface of the sphere. So if we're going to try and find the energy density inside the sphere, it means we're going to try and find it in here. Well, we know our energy density depends on the electric field. What's the electric field inside the sphere? That has to equal to 0. So the electric field inside a conductor is always 0. And then if you wanted to work through using Gauss's law, the integral of E dot dA is equal to Q inside over epsilon naught. All of the charge spreads to the surface because they all repel and they get far apart. So if all the charge is on the surface, there's no charge inside, so there's no electric field inside. There's no net electric flux. So the electric field energy density for R less than R is equal to 1/2 times epsilon naught times 0 squared equals 0. There is no electric field energy density inside of the sphere. Okay, next let's do outside of the sphere. Another quick sketch of our sphere. We'd like to find the electric field energy density out here. So this is a sphere with radius r. And the radius our conductor is capital R. So if we want to use our equation for energy density, we're going to have to find the electric field. This is a result that we know, but it's still worth taking a moment to figure it out. So Gauss's law says that the net electric flux is the integral of E dot dA, which is equal to Q inside over epsilon naught. In our expression here, the electric field dotted with the area element dA, we can figure out what that is. The electric field comes out radially everywhere. So there's our electric field vector. If we pick a small area element on the surface of our Gaussian surface here, dA, we see that the electric field vector and the area vector are parallel. So E dot dA is E times dA times the cosine of the angle between them, that's 0. So that's the integral of E times dA. Electric field is constant everywhere on this surface because it's a constant distance that comes outside. The integral of dA is just the area A. Area A means the area of that sphere. That would be 4 pi r squared. So that takes care of this part. The Q inside is the net amount of charge inside our Gaussian surface. That's the total charge on the conductor Q. Now let's put these guys together and we'll solve for the electric field somewhere on this surface. So E is 1 over 4 pi epsilon naught times Q over R squared. And if you prefer, you could write that as K, Coulomb's constant. Okay, from here, let's find the energy density. So we'll use our expression. It's 1/2 times epsilon naught times the magnitude of the electric field squared. We'll plug in our electric field. 1 over 4 pi epsilon naught times Q over R squared. That whole guy is going to be squared. 1/2 times epsilon naught, 1 over 16 pi squared, epsilon naught squared, Q squared over R to the 4th. There's an expression, let's just simplify a little bit. 1 over 2 times 1 over 16 gives us 1 over 32. We've got a pi squared down here, epsilon here, epsilon squared here, leaves us with epsilon in the denominator. And we also have Q squared over R to the 4th. So there's our electric field energy density outside the sphere. The next part we'll do is calculate the total energy. So we have the energy density. The next part we'll find is the energy.